Hello guys, welcome to Everything Metallurgy and welcome to day 49 of 100 days 100 concepts. Today in this video I am going to explain you about fracture toughness. So what is toughness actually? So toughness is nothing but the amount of energy that is getting stored in a body before fracture. Okay, so energy that is stored in a body that is actually utilized for fracture is my toughness. Now fracture toughness is more or less same, but we call it specifically fracture toughness because it not only explains you about the energy stored in the body before fracturing, but it also explains you that this fracture toughness is acting as a resistive force or resistance of a body to fracture. Okay, so this is actually important. Okay, so the amount of energy or work done in order to fracture a material can be explained by this concept of fracture toughness. Okay, so how to calculate toughness? Simple, right? We know it is nothing but the area under the curve until fracture, right? This is nothing but my stress strain curve. So in other words, if you want to write it, so ut, let me write it, it can be written as integration of 0 to epsilon f. So I am writing epsilon f, which is nothing but the final strain or the strain at the fracture point. Okay, so sigma into d epsilon. This is how you can actually calculate. So this is one kind of approach from mechanical testing. Okay, so this particular principle uses mechanical testing phenomena, okay, finding stress strain curves and all the stuff. But there is one more kind of approach via fracture mechanics approach. Okay, there we say something called K, which is stress intensity factor. Okay, so K is actually my stress intensity factor, which is written as K equal to Y sigma root by A. Okay, so this K is my stress intensity factor, Y is a material constant. Okay, usually for metals at least this Y will be equal to 1. Okay, sigma is nothing but the applied load or applied stress. Pi, we all know A is nothing but crack length. Okay, so using the concept of stress intensity factor, you can define fracture toughness. So basically what happens in fracture? The process of fracture actually involves 3 steps. In step 1 there will be damage accumulation, step 2 there will be nucleation of voids or nucleation of cracks, which we also call crack initiation, and finally in step 3 there is crack propagation. That means the crack actually grows. That means whatever cracks that are present in your body will not be having the same length throughout. Obviously fracture means what? Separation of two bodies, right? So to that, to make sure that that separation is taking place, your crack must propagate through the body. Okay, that means if A naught is my initial crack length, it should always increase on application of my loads, right? This is one thing. Now what you must know is when A naught reaches its critical length, so usually critical length is nothing but the maximum crack length that can be sustained in the body before fracture. So when A naught becomes AC, my stress intensity factor is also becoming Kc. So where Kc is my fracture toughness. Okay, so when A naught, the initial crack length, reaches its critical length or maximum crack length, my stress intensity factor also increases to its maximum stress intensity factor, which we take it as fracture toughness of that particular material, right? Now we also have one more interesting thing that you have to know. We have different modes of loading. Okay, we have different modes of loading. So let me write mode 1, mode 2 and mode 3. Okay, so mode 1 is called crack opening mode. Mode 2 is called in plane shear, okay, or it's also called sliding mode, and mode 3 is called out plane shear mode. Okay, so in mode 1, actually let me take a body which has a surface crack, okay, and I am applying longitudinal stress. So what is happening? My applied load is perpendicular to the crack, so the crack will tend to open. So that's why it is called mode 1 or crack opening mode. So the fracture toughness which we get from this this mode of loading can be taken as KIC. Similarly in plane, so in plane mode will look something like this. So let's say this is your crack, okay, so this is how your stresses will act. That means this is kind of shear but acting in the same plane. This is mode 2 or in plane shear or sliding mode. So this is K2C. Similarly mode 3, let me take a 3D so that you can easily understand. Okay, you see, so this is a crack over here and my loads are actually applied perpendicular to this particular body, okay, one on the inwards and one in the outwards. So that means you have two opposite side, something like shear only, but outwards of the plane. It's not inward, it's outward of the plane. Okay, so this is my K3C. Okay, so now there is a competition here. So we have three different guys, three different modes, three different fracture toughnesses, but what actually you have to represent for a body, that is a big question. So you would have seen already in some previous year questions or something that KIC is actually used to represent the fracture toughness of a body. Okay, why sir? Why only KIC will win this competition? Why not the other two? So KIC is actually low than the other two. KIC less than K2C, less than K3C. Okay, so what? If it is less, why only consider that? K3C is very high, why not consider that? The reason is that KIC, because of its low value, what happens is that the amount of resistive force that it can give is very low. Okay, so out of all the three different modes of loading, mode 1 loading has least resistive force to fracture, right? That's what fracture toughness is. Remember the definition. KIC means it is explaining you the fracture toughness that has been measured when you are applying mode 1 type of loading. Now we are telling that KIC is used to represent the fracture toughness of a body because it has low value. So this low value means that KIC has least resistance, okay, or any body has least resistance to fracture in mode 1 type of loading. That is why you are using that to represent the resistance of the total body to fracture. So let's say you are representing K3C for suppose. Okay, so you represent, let's say I have this aluminum body and I have K3C of let's say some 70 MPa root m, okay, some random value. If I use that material and apply mode 1 type of loading, what happens? It cannot give me that much of resistive forces. It cannot give me the resistive force equal to whatever I am mentioning, which is K3C. No, if you are using in K1C, what happens? If you are using in mode 1 type of loading, it will fracture simply even less than whatever value which we have over there, which is my K3C. So always it is easy for us to explain with the help of least resistive force. So if you are taking this least resistive force KIC in whatever mode of loading, let's say mode 1, mode 2, mode 3, my material will only fracture when this particular KIC, this resistive force has been overcome, has been overcame. Okay, I hope you understood what I am telling. So the reason to choose KIC to represent the fracture toughness of a body is because it has least resistive force. So for any body, it is safe to explain you with least resistance that the body can give you for the fracture, right? So yeah, I hope you understood what I am explaining. So thanks for watching. So do watch our website everythingmetallurgy.com, and we are soon reaching a century. Okay, so nearly 100 trustworthy students we have gained. So thanks a lot. So do check out everythingmetallurgy.com to avail one of the best Gate Metallurgy video course as well as test series for Gate 2021 as well as Gate 2022. Thank you guys. Thanks for watching. Meet you tomorrow with one more interesting concept. Thank you.